Welcome to our discussion of graphs of functions. Here are the objectives for this video. Feel free to fast forward and skip the stuff that you already know. All right, so graphs of functions are obviously very important so that we can visualize what's going on and kind of understand the relationship between the x's and the y's. So how do we graph functions? Well, we can plot some points or we can use technology. Those are really our only two options. So if we're going to plot some points, we just have to remember that it's just going to be a whole collection of ordered pairs, x's and y's, or you can think of them as x's and f of x's. And all you got to do is pick a bunch of x's, plug them into your function, get a bunch of, f of x, i.e. y values, and plot those points. You just, got to do enough to make sure you can get the overall shape of what you're trying to graph. The more complicated the function, the more points you need. The simpler the function, the less points you need. i.e. a straight line, you only need 2 points, but a quadratic, you're going to need a lot more than 2. All right, so some examples, obviously the simple one, a linear function and constant functions. Those are very easy to graph because you only need a couple points. And in fact, with a constant function, you only need one because if f of x equals 3, you just have that horizontal line up there at the height of 3. All right, what about power functions? Things where we have x to a power or root functions, right? X to the 1 over n, square root, cube root, things like that. Well, if we're going to do those by plotting points, we're going to have to plot a lot more points. So some examples, x squared, x cubed, square root of x, right? Simple-ish, but still require a lot more points than just 1 or 2 like the previous examples. So you plug in a bunch, you can see, with a square, you do plus or minus, you get the same. With a negative, or sorry, with a cube. So even powered functions, plus and minuses are the same. Odd powered functions like the cube, they're not. So we're going to get different values for positive a half and negative a half. And then square root functions, of course, we can't plug in negative numbers, so we're only doing positives. And once we have all those, we can put the dots on the function on the Cartesian plane and then connect the dots and get the overall shape of the graph. But you should already know that x squared is a parabola, i.e. a horseshoe, right? X cubed is cubic, looks like a lightning bolt, and then roots, square roots and things like that, they're going to just look like half of parabolas on their side. All right, what if we want to use some technology like a graphing calculator? Well, I'm not a big fan of forcing everybody to spend a lot of money and buy graphing calculators. They're awesome tools to have, and if you have them, great. If you don't, there are free emulator tools all over the place. Just go out and Google search away for them. Texas Instruments offers a great one that works on Windows machines, I know for sure. I'm pretty sure it also works on Mac, Apple. Go to that hyperlink and just download the first file at the top. It's called exactly that, TI-83 plus SDK. Follow the prompts and install it on your computer, and you basically get an emulated version of the TI-83. When you install it and run it, it just opens this and you go, what the heck? So click here like you're opening a new document. Choose whichever version you want. I always just take the TI-83 Plus. It's the only difference with the Silver Edition is it looks different, right? Click OK. Gives you this. Again, you're like, now what? Right here for play. Push play, and then this will pop up in the upper left-hand corner of your screen. And now you have a TI-83, right? You can do standard calculator stuff, but then you can do all the fancy stuff like graph things with x squared, and then graph it, and there's x squared, right? So it's a very simple, easy to use tool as long as you know how to use the Texas Instruments calculator. And if you don't, just again go out and Google Texas Instrument calculator or TI-83, and you will find thousands and thousands of documents on how to use them and video tutorials on YouTube and all that stuff. Okay, if you don't want to use that, or if you don't have a Windows or a Mac machine and you're using a Chromebook, it should work on Chromebooks, but if not, you want to use an Android or an Apple device, like you want to put something on your phone or a tablet, there are all sorts of applets out there that will do it. My favorite is the Wabbit EMU. It's very simple to use, and it basically just turns your phone into a TI-84. The screen looks exactly like it, and you just touch the buttons like you would normally. It's fantastic. So you don't have to spend the money if you don't want to. Okay, so if you are going to graph it with technology, whichever one you use, it makes these things pretty easy, right? You can figure out what things look like really quickly. If you have to do piecewise defined functions, that's a whole nother ball of yarn. You can't really do them easily with technology. You can, but it takes a little figuring out. It's not as intuitive as you would think. You kind of have to graph two different functions on the same screen, and it doesn't really work. You got to restrict domains, and it's a pain in the butt. There are some really awesome online graphing tools that you can go to. So as long as you're on the internet, have access to the internet, because the nice thing about the emulators I showed you is they work when you're offline, right? You don't have to be online for that to work. It's a program that resides on your computer, and the same thing with the ones that are on your phone or tablets. But there are more powerful things for like defining piecewise functions that are online that can help you. Now, here are, I don't know why this slide is here. It's a little out of place, other than the fact that we're just reminding ourselves how to graph these things with technology. We've already seen these, right? But here's our piecewise function that we just defined up here, right? So piecewise function basically just says we have two pieces. We have this first piece whenever x is less than or equal to 1, and then we have this other piece whenever x is greater than 1. So if we come back here, right, here's our rule down here at the bottom. I'm going to make it bigger over here so we can remind ourselves of what it said. So on the left side of the function, right, from 1 and down, right, when x is less than or equal to 1, we get the parabola, x squared. So that's this shape. And of course, if we kept going, the parabola would keep going up here. But it's not defined over there. When x is greater than 1, we get a straight line, 2x plus 1, which is this one. And you can see we have a solid dot here because this is a less than or equal to, and we have an open dot here because this is strictly greater than. And the reason why we do that is to make this a function, right? Because vertical line can only hit it in one place, and if these were both a solid dot, if you drew a vertical line at 1, it would hit it in two places. Another version of a piecewise defined function, kind of one of the most common ones that you'll see, are what are called step functions. And step functions are called that because when you graph them, they look like the steps on stairs. And it's the greatest integer function, and there's also a least integer function, which is pretty much the same thing. It's just defined slightly differently. They're sometimes called floor and ceiling functions, but they all pretty much do the same thing. They take decimals and round them. The greatest integer function always rounds down, right? And then there's, I can't remember, it's called, I think the ceiling function always rounds up, right? So this one's called the floor function because it always rounds down. So you can see that, the greatest integer less than or equal to 2 is 2. So these little funny bars just mean take the greatest integer less than. So that would be 2. And then the biggest one, right, that's still smaller than 2.3 is 2. And then the biggest one that's still smaller than 1.999 is 1. So you see how we're always rounding down. Even though 1.999, if we rounded normally, how we normally just round in math, that would round up to 2. This is not a rounding function. It's a greatest integer less than function. So it's a floor function, right? It's always rounding down. So 0.002 rounds down to 0. Negative 3.5, this is where it gets tricky because on the negative side, right, if you're over at 3.5, you now have to round down, right, to negative 4. And then, of course, negative 1/2 rounds down to negative 1, right? So that's the greatest integer function. You'll see that in economics a lot. And here's an example of it, right? And then here's the graph of it. And you can see that all the way from 0 up to 100, you kind of have this fixed cost. And then as soon as we get a little bit more than 100, it jumps up to a new fixed cost, right? If you're at 100, it stays here, right? That's why there's a solid dot here. And then as soon as you get a little bit more than 100, it jumps up here. And now you have this fixed cost until you get to the next marker, right? And then it jumps up to that fixed cost, and then up to here, and then up to that fixed cost, right? So that's what I mean by, you see it a lot in economics because a lot of times costs aren't linear, they jump. The first 5 things cost this much, and then the next 6, 6 through 10 cost another fixed amount, and so on and so forth. Okay, a function is continuous if there are no breaks or holes in our functions. Obviously, the first two we saw were continuous, and the last two we saw weren't, right? There's all sorts of breaks and holes in that thing, and there's one break and hole in that one. And if we go up to these, that one was continuous, right? This one is also continuous. It doesn't look like it, but it's because we're zoomed out. And then these are all continuous, right? Because there's no breaks, there's no gaps, there's no holes. All right, now if we're trying to determine if things are continuous or not, we pretty much have to graph them unless we know something about functions. Certain functions are always continuous, i.e. all polynomial functions, things that are just made up of powers of x are always continuous. Step functions obviously are never continuous, things like that. And then if we want to figure out if something is actually a function, not a continuous function, but a function, we can use the vertical line test if we can graph it, right? So we graph something, and again, if the vertical line hits it in more than one place, it is not a function. But what if we can't graph it, right? Well, then that's when we have to just know what kind of things are functions, and if that doesn't help, then we have to kind of look at values and find out if we have any matching pairs, right? Where we get two y values for one x, then that's a problem. All right, here's some more examples of the vertical line test. We can see that if we want to see if it's a function or not, the first one obviously is not, second one is, third one is, fourth one is not. All right. If you have things memorized, you know what functions are, if you know what y equals x squared looks like, you know it's a parabola, you know it's a function, so you don't have to go through all this rigmarole. But if not, then if you're trying to determine if an equation is a function, the first thing you have to do is solve for y, and then think of it instead of y equals x squared, you think of it in function notation as f of x equals x squared, and then you can figure out if it's a function or not. So for these, right, you would solve for y. The first one, really easy, x squared plus 2, and we know that's a function because that's just a quadratic, a simple parabola. But then for this one, when we solve for y, all of a sudden we get plus or minus. So you see how now if I plug in one value for x, I get y equals plus or minus that. I get two values for y, and it's not a function. Right? And if we graph them, the first one was the parabola, like I said, and the second one ends up being a circle. Right? I know it looks more like an ellipse there, but that's just because the graph has been squished. And of course, that fails vertical line test. So like I said, if you know certain characteristics of functions, if you know certain families of functions, you know whether or not they're continuous, you know whether or not they're actually functions or not, you know their basic shapes, and these are very helpful. Right? Linear functions, simple, easy. X squared, x to the fourth, you can see that all even powers look relatively the same, right? All odd powers look relatively the same. Root functions, right? So if we have even roots, so square and fourth, again, it looks the same. We only get half of it because we can't take even roots of negative numbers. And then cubes look relatively the same. You'll notice that these are just these on their side, right? If you take this and turn it to the right and this and turn it to the right, you get these functions, right? So they're basically the same because they're kind of inverses of each other. If you think about this, if y equals the cube root of x, if we cubed both sides, don't we get y cubed equals x, right? Y cubed equals x. But if we go up here and if we trade places, instead of y cubed equals x, we have x cubed equals y, we get this, right? So you're basically just swapping places. You're trading places with the x's and the y's. And so instead of the input being here, your input is being here, right, up and down. And so everything's been rotated by 90 degrees. So that's basically what's happening. And we'll talk more about inverses later. But that's why they look so similar. Then, of course, we have the reciprocal functions. Basically, anytime you're dividing by powers of x, you always have breaks in them because you always have places where you're dividing by 0 and you can't divide by 0. So you always have vertical asymptotes where you have to restrict your domain and you can't do those things. And then, of course, you have, kind of the oddball functions like the absolute value and the step functions. And if you know all those different families, it just helps you do these things quicker.